So do you all know what are probabilistic algorithms? Of course, because well, in pseudo-anonymous. Let me just remind you still. Also focusing on the one side error. So the class RP I actually even made a mistake before I said I made a mistake. I just couldn't stop. Okay, is the set of languages, or RP is the class of languages. Languages for which exists. So let me L, I'm fixing something in the class, for which there exists a polynomial time algorithm. So it's a randomized algorithm, so probabilistic, such that, well, for any x which is in the language, the algorithm given randomness R will accept the probability 1/2 at least. And for any x not in the language, the algorithm will reject. Right. So again, just reminding you what are one-sided randomized, one of them, one-sided randomized algorithm. Bigger than that. No, that's fine. Good. That's a good point. If it was two-sided, I have to have like a 2-fold and 1-fold. But that's enough. Let me, because this is 0. So again, so let me, the half is really, it could be important. The epsilon. Right. Once, so RP is the class of all languages for which there exists an algorithm, an efficient algorithm, but it can be randomized, and it can have what's called positive, false negative, but not false positive. So what do I mean? So if x is in the language, you may falsely not notice that. Right? You may say, well, it's not in the language, but that will happen with probability at most 1/2. So probability 1/2 you'll accept. That 1/2 can be any constant that you want, and even one of the Boolean. We'll talk about that. So it could be even small, where n is the length of x. The input length. But if x is not in the language, it's really hard to. If x is not in the language, then you should never accept. Right? So you don't have like a false positives. You don't falsely think something positive about x. Okay. It's a little confusing. What's
drug
right, exactly. Exactly. You don't want in drug trials, you don't want to accept something that you yeah. But I hope the half is valid. And the point is, if you have if you have some flexible probability like 1/2, it will just repeat it twice. And accept if one of them accepts, even if one of them accepts, then okay, so if x is not in the language, you won't accept, that's fine. But if x is in the language, the probability that you will miss it in both times is 1/4. It's half times a half. So the probability you will fail is 1/4, so you will succeed with 3/4. And actually, I want to touch on that point. That's the whole point. Error reduction. So the theme here is error reduction. The title. So let me talk a little bit about that before we move to expanders. You can do that in a more economical way. So the 1/2 potential can be reduced to, let's say, 2 to the minus t by repeating t times. So then we just choose t random strings that's required for the algorithm, run the algorithm with these t strings, and accept whenever at least one of them accepts. Right? So just namely you accept. So you accept if and only if at least one of the t iterations seven. Right, and the point is that if x is not in the language, you can repeat as much as you want. Whoever accepts, it's fine. If x is in the language, then each of them will fail also probability at most 1/2. Then, because of the independence, the probability that all of them will fail is 2 to the minus t, and that's the only reason you will fail. Probability failure is close to the minus t. And, you know, you can actually get it exponentially. Right, not just polynomialism. If you care about running time, yeah, well, forget it. Right. Let me just, you can get it exponentially small because you can take t to be like poly n. The running time is getting a factor of t because you run it t times. But if it is poly n, you are still fine, and you can get the error exponentially. Right. However, the amount of randomness that you use, we care about randomness. We are doing pseudo randomness. So if you use R random bits, let's call it R even though it's the name of the string. R random bits, let's call it S. Okay, if you use S random bits initially, how many random bits you're going to use here? S8, not the. Exactly. Go next one. Good. Naively. So when you try to de-randomize an algorithm, that's like the main client of pseudo-randomness. Then you can't error reduce like that because it costs you more randomness. You would like not to add so much randomness, but sometimes you do want to have an error reduction. So you definitely want a way, you should trust me, that you definitely want a way to reduce the amount of randomness used, even at the price of running time, by the way, when you error reduce. So I'll show you two results. Both of them are really interesting, but the second one is like, feels like wrong. Feels like something wrong. This is the length of amount. The amount of randomness used for one amount of randomness used for one random bits required for one iteration. Yes. Oh, one iteration. So I mean, this question is actually interesting not just when you consider time. So you can look at algorithms, and that's actually what I'm doing a lot. The algorithm that run in low space, not just time. When you consider how much randomness mode you need, halting maybe space a little bit to get error reduction and so forth. So actually, it's like a triangle. There is like the error, amount of randomness, and then the other resources, time, space, whatever. I'm just doing time here because I don't really mind doing whatever. And time is like the most kind of natural for people. You understand time. You think you understand space. You don't. Space is really weird. You use. Okay. Oh, it's not paradox. It's a reduction. Later in the video, you'll see that. So just continue. So I'm going to give you two error reductions. What to do? They're incomparable, of course, otherwise. Both ways are expanded. We want to show you both because you use it differently. So in the first error reduction, you can see, we are going to get error from up to 2 to the minus t, or maybe 2 to the minus t over 2 or something, but it doesn't matter. You can get 2 to the minus t, and just fix it here. And the amount of randomness that you use is not the product of the two, it's the sum. like the resolution. Talk about in the lecture one. Right. It will be like a big log deal. Exactly, good. Exactly. That's exactly how we do. We're going to take another one. It's immediate for the eating. Let's see that. Very nice. I don't know. I mean, what you did in your head, you took the randomness, put an expander on them, fixed an X, looked at the bad set of strings, and looked if you want to avoid them. That's 4 steps. Not only yes, we'll do it. Yeah. And the second, I think it's even more interesting. We reduce have to, well, here we can only reduce it to something like 1 over Boolean. We can use it to whatever we want, but the running time will be this. So, say Boolean, but you know what the amount of randomness will be? Crazy. No, okay. No, that's why. Not this crazy. That's why life works. Efficient to de-randomize, right? Okay, one way to do that is to de-randomize the entire algorithm. It's 0, but that's fine. And then that's crazy, yes. You don't expect to be able to do that for time, maybe for space. But less crazy. S slash login, yes. Yes. Monetary reduction for free. Kind of crazy. The entire, I mean, I don't know if it's crazy, but if you believe that you can de-randomize them, it's 0. But it's still crazy. The running time takes only hits. For example, you cannot with polynomial running time overhead, you can get here 1 over exponential n and here only 1 over polynomial. So the running time if you get here is exponentially worse than that, but still that's okay. So let's see the first one. Exactly what you said, but I think you should see that. It is usually an exercise in the homework, but I thought maybe I should just do it because there is this class that we need to repeat things, and I think that you can do that, but it's really better that someone will emphasize the things that. So the fourth theorem. So the point here is that you have this language, of course, and then you are looking at specific algorithm, but also like let's fix X possible. Let's fix an length M. Yeah? So I fixed L, I found them, so there is an algorithm for it, basic one, and I'm fixing X. So that's important. I'm fixing X. Okay, I'm looking at the randomness. The focus is on the randomness. So, in this set of size, the set of size 2 less, like the set of random strings that you can plug into A, I mean, of course, S depends on the input like X. Right? This can be a polynomial in the input. The amount of randomness used is bounded by the time you run, and that's polynomial in N. So you should think of the length of X as N, and S is the poly N. You can just draw something that it doesn't really matter. So these are random strings. Some of them are good and some of them are bad. Like, actually, if X is not in the language, all of them are good. Because you never accept. So that's good. If X is in the language, you know that there are some little R's here that will make you accept even though you should, make you reject even though you shouldn't. Right? So these are the bad set. This is the bad set. So B, with respect to X, these all the strings are all the choices of random string such that AXR rejects. You want to accept, right? But some string will tell you it's not there. X is not in the. Now, when you do independent samples, like in the naive way we did, you just sample like T independent elements here, and the bad event was all the elements lie in B. And that the probability of that to happen is, of course, the density of B, which is half to the T. So what we want to do now is to actually use dependent samples using expanders. But there is no expander here. What you do is you artificially put an expander. So you did a lot in your head. You did a lot less. I just assumed it would be more. Like, no, that's good. That's for intuition. So what you do here is just a set of strings, random strings, 0, 0, 0, 0, 1, no structure. But what you do is just say, okay, I'm just going to put an expander here. Expander should do that. Should definitely doesn't have that. And so let's say you put a degree D expander on 0, 1, 2, 3. And you just, there is a parameter D, you take the best expander you can, it won't matter much here, but take, say, the best expander you can, and you think of the vertices as the random string that you can feed to A, and the edges are, have nothing to do with A, something about you. It's something that you added to the system. And now, so what's your suggestion? How would you get T random strings using the expander? Just one, right? So instead of sampling T R's independently, we'll use a length T in number of vertices, random one. So, right, the first vertex will be completely uniform, but then the rest will not. So, for example, just count how many random bits you use, just to make a sense of it. So, the first step is completely uniform. You require S bits, but it's a graph on 0, 1 to the S. And then the remaining, so you have T minus 1 steps, and then you need to log the degree, right? This is the amount of randomness. Also note something else, regardless of anything. This graph is huge. Like if S is poly n, this graph is exponential in size. So this is why we need strongly explicit construction. You can generate a graph. What you want is to be able to take a random walk. So choosing a vertex at random requires S times which is poly S, which is fine. And then picking a neighbor shouldn't depend on the entire graph, only on the degree. That's why you really need strongly explicit graphs. Otherwise, this is exponential running time. Space. And in space, right. Also in space. And in space, it's actually even more delicate. Well, I don't know. Maybe it's less delicate, but we achieve more. So we require more delicate stuff. In time, you can never really do anything. You can prove, and sometimes it's part of this kind of process, that if you want to de-randomize RP, show it's equal to P, you need to do things that no one will do. Like prove circuit law bounds that are like way beyond reach. But for space, there are no barriers. You can actually do a lot. Even from the 70s, you have to do a lot. So it's different. But anyhow, I rather not say. Is space more often than time? Yeah, right, in a sense. But we know how to do more. So at the time we are at, improving that requires more. I mean, even the current things that we do are more subtle than what we do for time, because we do nothing for time. We don't know how to do anything. And for space, we understand it better. It's really interesting. But let's stick with this. So what's the bad event? So when will our algorithm, which is really just what it does, right? It's sample an entity on the wall, apply A, both A with X and every vertex in the random string sees, and accepts if one of them accepts, right? So the only problem is that what happens to the random walk? Right. Once we are out, we're happy. So the only problem is that we'll see something like this. Exactly. So the bad event is that V1 up to Vt, let's call it, maybe R1 up to Rt, just R1 to Rt are in. That's the problem. Or maybe just two. The set is in TB, but then the expander, exactly, the expander hitting property tells us that the probability of that event, despite the many dependencies between them, is at most, well, the density of B, which is at most half, plus omega, which is the parameter of the expander, the t. Actually, we had like t minus 1.5 here, but I don't mind. That's fine. And so you see, even it's not really even like too critical for omega to be small. Once omega is like 1/4, you're happy. I made a lot of fuss about omega can be like 1 over square root of d or 2 over square root of d and something like that. For that application, it doesn't matter at all. Once you have omega which is 1/4, whatever you want which is smaller than 1/2, you're happy. So taking g, the graph, to have omega which is 1/4, will give you like maybe 3/4 to t, which is fine. You can repeat a bit more and get it to the 2 to the minus t. Now the degree is constant. I mean, there are constant degree expanders with that omega. Right? It's a very not too demanding omega. Right? Do you remember this whole story that I told you? There is the 0 here. There is the 2 square root of d minus 1 normalized like that. There's d here. This is Ramanujan. This is the zigzag which we'll talk about. So this is extremely difficult. This is difficult. You want like something here, like d over 4 or whatever. Omega to be 1/4. 1/4. So the scaling is bad, but you can understand that this is much easier to get than though. So even that expander, that kind of full expander will do the job. With constant degree, you can have it. And then the number of random bits, right? So it's s plus t times log of whatever the degree, it's constant. So it's s plus 4 of t as it is. And if you want 2 to the minus t, you just take a bit more, it will affect the order a little bit. No brainer. Good. Did I erase it? In the second one? Any questions? Why erase any chance to ask any question? Because we erase the entire material. Last question of how to do. Okay. So the second error reduction will actually help you a little bit in the homework. So no, I'm not going to use the homework, but so in the homework, what you showed / we showed the expander mixing lemma, just to tell you a bit about it. This is the expander mixing lemma. It tells you that if you have any two sets, S and T, expander set of vertices, then the number of edges, this is the number of edges going between them, the number of edges going between them is what it should be. Not only what it should be. So think of a random graph. What would happen in a random graph? So in a random graph, if you have a set S and a set T, then think of S from the point of view of S. Every vertex in S sends like fillers, the edges somewhere, maybe into random. So you have S times D edges leaving S, and the probability that each of them will hit T is T over N, N is the number of vertices. Right, so that's the number of edges you expect to be between S and T. Because you throw this many edges from S, each of them will fall into T with this instead of a heuristic thing. So this is the number of edges you expect. It's not the expectation, you can make it an expectation to take a random roughly, but this is what you expect. What should happen? Random. You should think of expanders as imitating random. That's at least. Now, if you're just going this, I like this division a bit better. If you divide by d and n, then you see that this d goes away, and you have an over n also here. So you get exactly this expression. You get exactly. So let me just do it. It should be roughly mu of s times mu. Because when I divide by d and n from this side, I get this. From that side, this d goes away, and you get an over n here, which is exactly mu of s times mu. So that's what you expect. And the expander mixing lemma tells you that you expander graphs will meet your expectations. Like the only problem is that there will be some deviation of omega, So the better the expander, the lower the deviation. Times you can actually also benefit from the fact that these sets were small. Like if mu of s and mu of t are small, you get an even better result. In the homework, you also have like times 1 minus mu of s, 1 minus mu of t, but I don't do that. I'm just going to use the weaker one. It's the density. Mu of s and this one. I'm using the notation from the homework. Okay? I guess we didn't prove this yet. But let's use that. So the first thing we have to do is to figure out what's the new algorithm. Right? We're not going to take random more. We don't have randomness. I mean, we can't use more randomness than what the original algorithm used. We can't take random more. The only thing we can do is sample a vertex, essentially. Sample a vertex. Right? In the graph, you have less random bits, so maybe you can do something else, but the one thing you probably will do is sample a vertex. Random. But then you don't want to just apply the algorithm of that randomness, because that's the original algorithm. What do you suggest?
You can decide on which edge to go. Guess heuristic and take the smallest neighbors doing that.
Okay.
If we are the smallest neighbor, then take the biggest. I don't know.
No, good. So I'm going to do something similar than what you said, but in your direction. I'm going to sample a vertex, and I'm going to run the algorithm with the randomness corresponding to that vertex and its neighbors. Just neighbors, all neighbors. So it's what you said is choose some of the neighbors, right? So I'm just going to do the more naive thing. I'm going to choose a vertex at random and run the algorithm with the randomness corresponding to the vertex, but also run it with all of its neighbors. It's in the lines of what you said. But I'm not going to do heuristics about how to choose the neighbor, just going to do them. No randomness.
Okay. This is not in the NP?
No, I'm choosing a vertex at random. And then I'm going to run the algorithm on with this randomness and with this randomness. This random sense. It's in P, in output. I mean, it's not there. I choose this vertex, but otherwise it's deterministic. So the algorithm is sample R uniformly at random, and except if and only if AXR accept or one of AX R prime except for R prime in the neighbor set of. So just running it over all of these. So now what's the bad event? So say again, B is the bad set. As before, B is the set of all strings that make A reject even though it shouldn't. So what's the bad event?
All of them are in B.
Exactly. That R is in B and all of its neighbors are in B. This is bad. So you're only worried about this set C. Let's call C the set of all R's that are in B, because we also check R. So if it's not in B, we're happy. That also its neighbor set is contained in B. Right? Because only that's the problem. If there is at least one neighbor or R itself are outside of S, we're happy. Right? Because we'll catch it. And now, just a one-line thing. I want to show that C is small. That's what I want to do. I'm going to use it, do it using the expander mixing lemma. It sounds weird. How should you? The expander mixing lemma talks about the number of edges between C and D, but it also implicitly talks about the size of C. And so if you know that there are many edges, you can gain something out. So you'll see it now. Usually people think it doesn't make sense to use it because they don't care about the number of edges. Actually know the number of edges. And that's good. If you know the number of edges, you can figure out something about the edge size of the set. Right, so what's the number of edges between B and C? Like every element, every vertex in C has all of its neighboring B. Right? And C is contained in B. So how many edges you have in? And how many edges are between C and B? All of them, right? Like for every vertex in C, all of its neighbors are in B. Exactly, D times C. C is the container. D times C. And that's kind of a lot. There are too many edges. So C cannot be isolated. So plugging that in the EML, so we have D times C, that's C, divided by D times M. So that's already C, which is the density of C, which you want to show small. Minus density of C times the density of B is at most omega times the density of B times C. And because I can't do it like that, let's call beta the density of B and gamma the density of C. So here you see gamma sitting here. It goes away. Here you have beta gamma. And here you know it's at most omega times the square root of beta. So you can divide by square root of gamma. And this is always larger, right? So we don't need it, right? In this case. We don't know, but now beta is smaller than 1. Actually, beta is a half. So beta is a half, so this is just gamma over 2. It's supposed to half. So let me be careful. So the square root of gamma minus times 1 minus beta is most omega and square root of beta. I just divided by square root of gamma. And so square root of gamma today. And you know what? I don't even mind. So if that's true, okay, now if that's true, then beta is smaller than 1/2. So I know this one. Direction. So what you get, so you multiply by 2 and take a square root. What square? What you take is that gamma is at most 4 omega squared beta. So you see, whatever the size beta was, it's a half. But whatever beta was, the gamma is omega squared smaller. So right. Right. So let's keep it simple. Right. So then beta is more than 1/2. This is 2 omega squared. And that's the error. And that's the error. That's already referring to C, that's the error. Gamma, exactly gamma. So this is the error. And you know that there are good enough graphs that now you need a good enough graphs for which the degree and omega, so omega is roughly 1 over square root of degree. This means that this is roughly, you can have graph here in the really good graph, one something. Omega 1/4 doesn't suffice here. But because the error decreases with omega. So if you remember, omega is roughly 1 over square root of d at the best. So that's the relation. So the error decreases with 1 over the degree, which makes sense. You check things for free. The running time gets a hit by a factor of d. Because the running time is, check all the neighbors, d. So the running time is like inverse to the error. That's why you can't take it exponentially. You can take it polynomially. It's usually what you do in this case, you take d to be like poly n. There will be 1 over poly n. The running time will be poly n times what it was. And one thing to note before we go is that in this case, actually, an expander with degree, which is polylogarithmic in the graph size, it's poly n, but the graph size is 2 to n. So the degree is polylogarithmic in the graph size is very useful. It's not only the constant degree expanders are useful. Here, all you need for good error reduction on poly n is graph whose degree is polylogarithmic in the graph size, which are easier to get. You can do it with kilograms. So we'll talk about those next time. So next. So anyhow, this is also an example of when the constant degree is actually not relevant. You need this one. See you after the break. I'm here for questions if you have questions.